Good. Okay, then we can start. Hi everyone. This is my PhD progression presentation, and it's about verification of natural language processing. It's before done by me with collaboration of various other people. So just a bit of an introduction about NLP or NLP system. This is just general, and it's what we're going to use. NLP system can be broader or different, but this is just a summary. So, of course, as input, you will have sentences. Well, this one, the robot. And however, neural networks need inputs that are constant in size. So sentences are not sentences on like characters or words, and you want to give an arbitrary sentence to the system. So you need a way to feed these sentences and transform them to, at the same size, to then pass them to a neural network. For that, we're going to use embedders, that is the standard for NLP. There are various types of embedders. We are not concerned about what we use right now, but the point is they take a sentence or words and they produce a vector of always the same size with some numbers inside, and this is magic for them. After that, we can pass these numbers to a neural network. As you probably all know, as you've seen, at least some neural networks, it's just normal neural network. It can be any hidden layer, it doesn't matter really here. And finally, we're going to get an output to this decision. In this project, we are concerned with classification tasks, so it's going to be a class. So, why did we want to do this work? What is it about? Neural networks are fragile, and that means that they are susceptible to adversarial examples. What are adversarial examples? An adversarial example is modification of an input. It can be a modification of an input, a small one that is not perceptible by a human, in this case, that changes the classification of the network. The network classifies it incorrectly. So this is the most famous example. We have an image of a panda, the network classifies it correctly. You add some noise, and you get this other image that you can't see the difference, with your eyes. But the network misclassifies as a gibbon, or doesn't really matter what, but misclassifies. Now, what are adversarial examples in natural language processing? As we said, we are working with sentences or words. So we can classify adversarial examples in a few different ways. There can be character perturbations. You can see that it might change, and it might be added or removed. There might be word perturbations. Similarly, you might add a word or change a verb, the tense of it. You can do a few things. And lastly, you can also do sentence perturbations. That can be considered like a sequence of word perturbations as well, if you'd like. But the important thing here is that you can immediately tell that they're not imperceptible. You can see the difference with your eyes. What's important here is that they don't change the semantic of the sentence. So the sentence is inquiring if the system is are you a robot? And this is still the same intent like the last one. You can tell the difference, but the intent is the same. The semantic doesn't change. Now, why do we care about that? Well, there are some critical applications, like in the legal side, there are laws that say if a chatbot is asked or a bot is asked, it can deceive the user. So it needs to abide the law and it needs to recognize the intent, and it needs to, when it detects that, it can say, yeah, no, you're talking to a bot and not a human. Also, there can be other reasons like safety. For example, in the medical field, you want to find and classify, correctly if the user is asking medical queries or urgent medical queries, or you can think about some safety critical applications. So what is our approach to this problem? We want to verify the NLP system. What does it mean? It means when I ask or when I input a sentence with the intent of asking a robot, or if it's a medical sentence, a medical query, we want the system to robustly classify that and tell me, ideally, 100% yes. I guarantee you that I will understand the intent. Now, it has some challenges. For example, here already, the embedded function. Usually nowadays it's a transformer. It's a big neural network, state of the art, and it's kind of too big and difficult to verify for the state of the art verifiers. Kind of big. So instead, we're gonna try to verify the neural network that is on top. That is a small one. We created is actually a 2-layer neural networks, and we use that as a proxy, as a discriminator. So in parallel with the system that may be a chatbot, you have also this one. The input is sent here. If it detects, the idea is if it detects the intent of your robot, then it will say, yes, I detected this. My system, rule-based maybe, will output the proper answer, yes, saying, yeah, I'm a chatbot, and what I need to say. So we're just gonna verify the neural network, or calculate something like that. Now, usually, what's been done in neural network verification, and most of it is about images, so computer vision, is the epsilon model. This is the most common concept, and basically you have your input. In this case, an example from the image dataset, you have this image of a 7, and you modify the pixel by maximum epsilon distance, and you get some other 7s with slightly different pixels. And what you usually do, it's called, in this case, epsilon model verification. You ask the verifier, I give you this input, this epsilon model around it. Can you guarantee that in this subspace, I will only have the class number 7 in this case? And we can use this naive approach in NLP. Naive in NLP here. It's not naive. And that's what we initially did. However, there are some obstacles to that. Mainly 3, we can say. Epsilon bonds. So you see this image. The red dots are from the input from the training set, so what we know. The blue dots are input that might be from the test set or even somewhere, but we don't know them. The circles are epsilon bonds, and of course this is an example, but it's kind of true. Epsilon bonds mostly don't contain any meaningful sentence. Of course, you can change the size of epsilon to like a big epsilon that contains everything. But let's say epsilon bonds that are small enough to be verified don't contain many unseen inputs. So they are not, we think they are not the best to work with for NLP. Furthermore, semantic similarity does not entail geometric proximity. That means that if you have two sentences that are similar, like are you robot, are you chocolate, when they get embedded, they might not be close together in the embedding space. And this is a property of the embeddings. We cannot do much about it, at least at this stage. And we have to take this into account when we try to verify. Also, generally neural networks are not very robust by default on normal training, so there is a need to be trained for safety and logical, to satisfy logical and semantic properties. So we propose some solutions to these obstacles. For the first one, we create hyperrectangles instead of epsilon balls. Actually, the first thing we tried was creating a convex solve because it is the tightest thing we can add around inputs. And because ideally, the best outcome would be I enclose all my input of such class, and I can verify that in such subspace, my network will always output the correct class.
This is an analogy of the limit domain. The limit domain.
Yeah, then we have some similarity with that. And however, it was not feasible because embeddings are in high domain, in high dimensions. So it was computationally infeasible to calculate the convex series. So then we decided to go for the closest hyperapproximation, overapproximation, that is the hyperrectangles. Now, as you can see, this is not amazing, could be much better, could be much tighter. So we also made some geometric manipulations to try and get better results. So the first thing is we try rotating the data. So you can see, if you rotate the data to align with the axis, and then calculate the hyperrectangles around them, it is much tighter and you have less white spot, less noise. And that's proved to be very much effective. Also, another problem is that these images is different from the previous one. I know it seems the same, so the previous one was red and 2 points, this is red and blue. Red is still input points from the class we want. Blue points are the negative class, another class. Could be many class, could be one, doesn't matter. It's not exactly one. So the problem is, if we calculate the hyperrectangle around our positive inputs, we also end up containing some of the negative ones. And the verify will never output, yes, this is verified, because it already has some inputs from the opposite class inside. So this is the problem. We need to find ways to exclude all the negative points. One such way is just to shrink the rectangle to exclude the negative points. So you see this one is the smaller and not includes positive points. Do you have any questions until now? Okay. So another thing we can do is clustering the data and then calculating hyperrectangles around each cluster. So they contain fewer points inside, and there's a higher chance that they don't contain any negative points. And of course, if some of them contain negative points, you can just discard them with a lot more. Okay, in practice, this is also good because generally these hyperrectangles are quite big and are kind of too big to be verified yet. So it helps to have a lot of clusters and smaller hyperrectangles around them. But we're going to see that later. Another thing we can do is to take into account the second obstacle that we found, is to explore spaces that cover semantic similarities. So how does this work? The red dots are still inputs of a class. The green ones are actually perturbations of that input. They can be character perturbations, word perturbations, sentence perturbation, any perturbation you can imagine. The idea is you take an input, you perturb it a few times with the same perturbation, with different perturbations is up to you, there is room to explore. And then you create hyperrectangles around those. This produces much tighter hyperrectangles that can be thought as epsilon ball alternatives. They can be similar in size to epsilon balls, while the previous one are much bigger, like orders of magnitude bigger. And they can be thought as, okay, let me try to verify that my network is robust against this kind of perturbation instead of like general perturbation. Lastly, to take into account the third obstacle or third problem, we do robust training. In this level, in this work for now, we have two ways of doing that. Data augmentation, that is the first one. You take the original data set, you perturb it as many times as you want. You combine these data sets, and then you train your network with that, and you will get the outcome. The other one is adversarial training, that is a bit more complex. It takes into account geometric properties of the network or gradients. So you have your original data set, you feed it to the network, you get the gradient, you get the worst case perturbation for each input, and then at each epoch, and then you feed it back along with the original data set. So each epoch, instead of having original data set plus static perturbations that don't take into account the weights of the neural network, you will have more intelligent, let's say, perturbations, like every epoch has crafted to be the worst case possible, at least locally. And that should produce a much robust network. Now, we designed a tool called Antonio that includes all this pipeline. It is from start to end. It is modular. You can change everything. It's dataset or preparation or transformation or model evaluation agnostic. Basically, the idea is, or the flow is, you have your dataset, and then you can create perturbation dataset. For example, in this case, you can attack it with word attacks and character attacks, many different datasets. And then you embed all this. We are using sentence BERT. It is indeed a transformer. It is state of the art for sentence embeddings. Then we apply rotation. And we also apply dimensionality reduction. We've seen that helps. And sentence BERT is number of dimensions of the embedding space of the vector is 384. It's very big. We scale it down to 30 with PCA. But you can have as many transformation, geometric, or any kind you imagine in place. Then we create the hyperrectangles. So we will have like a trans hyperrectangle, some cluster of hyperrectangles, epsilon cubes as well. Well, yeah, before I talk about epsilon balls, because that is what is usually used in the verification of neural networks. However, if you really go and look at that, it's actually epsilon cubes because it's easier to calculate and work with that. But it's the same. It's the same ring. And then we also call it hyperrectangles on attacks. They are just, if we go back, they are just this semantic hyperrectangle. After that, we can train our networks. We can have a base network that is trained normally on the original modified dataset with normal training. Then we can have this last two, for example, that is augmented data augmentation. So it is original dataset plus virtual dataset, and you train the network with that. And these one in the middle are the adversarial examples, the adversarial trainings, sorry. How do they work exactly? So we said that the network tries to calculate the worst possible counterexample and feed it back to the network, but it needs to have some restriction. It can't just be arbitrary one. Usually, in the classical case of epsilon balls, you take the worst possible perturbation inside the epsilon ball, because you decided that that is where you want to work after that epsilon maybe the image change too much and you don't think that's a valid counterexample. Here the same, so we have the epsilon ball just to for comparison, and we have also the other rectangles, but the idea is the same. We take the rectangles and with the gradient, we calculate the worst possible case from inside those rectangles, and we keep them in the given level. So they're just not just arbitrary worst case examples, but from inside the rectangle. And finally, we have three evaluation metrics. We have accuracy that you all know. You take the original dataset, well, the test set, so unseen inputs, and you calculate how many the network gets collected. Attack efficacy or attack accuracy, same idea, but with perturbed inputs. You perturb your test set, and then you feed these perturbed inputs. You still know what the class is, what the output should be, and you calculate the accuracy of that. And lastly, verification. This is probably the most important metric for us. And it is asking, verify. If I give you this network, if I give you these inputs, and if I give you these hyperrectangles, everything contained in these hyperrectangles, is it going to be classified correctly by our method or not? So we have initially used only one verifier, that is Aaron, that is an abstract interpretation verifier. It has the advantage to be very fast, but since it's abstract interpretation, it tends to grow exponentially with, at least to grow with the more neurons you have, the more layers you have, and it gets less precise. So it's not very precise, but it is fast. Then we also used Marabu, that is another verifier, and it's not abstract interpretation, it's based more on SNP solver for a part of it. It is very slow, but it is precise. So it calculates correctly every transformation that the input for the hyperrectangles has to go through the neural network. every layer, every neural application function, etc. But as I said, you can put any verifier you want. Verifier gets better every year, and this should improve these results as well. So finally, here is a shared selection of results. It's here a lot more bigger tables, but these are the most interesting ones. We have just 3 networks. So this network is the base network. This one. And then we have an epsilon network. This one. And the word network is this one. So it's still adversarial training, like epsilon, or net rectangles generated on one attacks. So here, accuracy and attack accuracy, it's good that, for example, accuracy doesn't drop much for adversarial training, because it is known that adversarial training improves robustness at the cost of accuracy, usually. So it is still the case, but it's very minimal, so that's good. Attack accuracy, the base one is already quite robust to attacks our adversarial training network into a bit of that, and that's good, but it's not the main result. So the main result is for the verification part. So first, let me go to these pages here. These are 3 different kinds of hyperrectangles, or set of hyperrectangles. This one, hyperrectangles created using clustering, and in particular, we have 250 clusters. So we have 250 hyperrectangles. Each of them created a cluster. This one is hyperrectangles on epsilon, but that also means epsilon cubes is the same, because a rectangle can be a cube. So this is just a rectangle that in every direction, every dimension, it is epsilon. So we have one for each input. So the cardinality of it is the same as the length of the dataset. Same for this one, because it is created on every input. We take each input, we attack it, and create perturbations, word perturbation in this particular case. And then we create rectangles around input and the perturbations. So as you can see, the base network is not very robust. It's like 2% here, 3% here, and it's another one. And less than 1% there. We have some improvements with the epsilon neural network that we set up in epsilon neural network. Not much here, but the most notable improvement is here with 8%. This is the highest we could get with error on this dataset. And we can see that the word network as well gets a big improvement, although not as big as the epsilon one. So this one is zero. I don't know what this is. Now, this was very fast to play on my computer. Half an hour, I got all the results like this. Actually, hundreds of them, not only 3. And then with collaboration with Israel and Norway, I could use Marble on a big cluster, putting thousands of queries in parallel, and it took like 2 weeks. Well, 1 week to this dataset, so let's say 1 week. So you can see it's much slower, but as you can see, we get a lot better results because it's more precise. Sometimes, since it's that low, it times out. That's why you see here, for example, a smaller number than the parent. It's most probably for the timeout. But when it doesn't, for example, here you can get an 18% up from 0.36%. That's another improvement. And the biggest one is on this one. This one was word attacks were just very good. You can verify 45% of the upper rectangles. We also have results from another dataset, the medical one, as I just briefly talked about in the beginning. They're not reported here, but they are much higher. So this dataset might be even a bit challenging for this task. So what's some conclusions about this? Epsilon ball or epsilon field, as we initially thought, is not very good in NLP, at least in this example, to be used as to be verified. This column and this column, especially this column. However, training with such a constraint, training with epsilon, almost in many cases yields the best result. Maybe because it's a more difficult constraint or property, but it has almost everywhere better results. They're still comparable to this one. So another found is that the hyperrectangles or trunk hyperrectangles, clustering hyperrectangles, they're much bigger than epsilon or perturbation hyperrectangles, and they're much more difficult to verify for that reason. So we can say in conclusion that especially verifying hyperrectangles on perturbation is some good results, and also the serial training really helps in that area. Something to work or what we can improve. At any stage of this pipeline, we can have some improvements. We can define more sophisticated attacks. So for this dataset, we have character attacks and word attacks. They work well because of this specific dataset. There was short sentences, quite specific. But for example, in the medical one, while character attacks work well as well, word attacks were very bad. They didn't make sense. So instead, we try to use more sophisticated attacks, like some state-of-the-art attacks that were sentence attacks that had better results. And more importantly, that they make sense semantically. We can also, also attacks year by year get better and more intelligent, or more sophisticated. We can also improve, change a dataset preparation, right? We have embeddings, preparation, dimensionality reduction. We can, for example, try different embeddings, other embeddings. There might be some embeddings that are especially modified to take into account semantic of sentences or any other properties that you want. Or we can even imagine some other transformation we want to apply. Well, we can try to think and define some tighter upper rectangles or even more semantically caring upper rectangles. That's another point we can work with. a very important one, I think, and that will be the main focus next, training. We use data augmentation at the cell training. Data augmentation doesn't help much. Actually, it makes things worse most of the time. The adversarial training helps a lot, as you see, but there are now ways for training methods that are even better, like certified training that kind of embeds a bit of verification into training, and it's a step further after adversarial training. And so that is probably the main step we're going to take after this. And then we can also change verifiers. Aaron and Marabu can be considered state of the art. Marabu for its own kind, yes. Aaron is very good, it's definitely up there. But in the last couple of years, there are even, well, on competitions, better verifiers like Alphabet Account, MMR, stuff like that. So, and every year they get better. So we can also try to use different ones to see if they even better results. Yeah, so that concludes my talk. Yes.
Yeah, so when you talk about more sophisticated attacks, I mean, the word attack sounds very negative to me. Is it also that to you an attack is basically maybe a mistake made by somebody and you want to kind of recognize that they actually have a particular intent?
It could be
kind of disregarding the fact that they made this mistake. So one of the things you could look at, I imagine, is that in cognitive, or at least in phonetics, there's notions like perseveration, anticipation, and juxtaposition. These are mistakes that a lot of people make in their everyday life. So you can think about as having any character change, but something that actually takes the form of an anticipation instead.
Yes.
See how a neural network, because it's more important, I think, to be robust against these not so arbitrary changes.
That is a good point. Our character attack, especially, but also word attacks. Well, character attacks are not just random arbitrary character attacks. We have 5 different kinds of them, but they are tailored around what people might actually do. So, for example, one of them is when you substitute a letter, you substitute it with the either left or right letter on the keyboard. So that's something that, right? So
because you assume type input that's spoken.
Yes. In this case, it's practically we are working with.
Yeah, so I know that anticipations and considerations. What happens there if you take let's say the first letter of the word it's coming, and you already use it in the words before that word. Right? That's called an anticipation because you're already thinking of the next word you're going to speak.
Okay, no.
That word starts with a B. So that's a particular one that human being often makes. So people know that.
Yes, but I don't think
so I consider attacks like that have kind of like a
so here we're taking every sentence as separate and we embed the whole sentence. So it's like there are 2 different sentences that are disregarded, like they're not. You don't take into account the previous sentence.
No. I mean, one. You can take the first subsequent words in the same sentence.
Oh,
that's how it works.
Oh, okay.
So if human beings speak a sentence, they're already thinking of the next words they're going to pronounce. And sometimes you get an echo backwards. So you already think I speak a word that starts with a T, and then an earlier word will all of a sudden also start with a T because your mind is already thinking ahead. Yep. It's the same. So these kind of mistakes.
That could be implemented as well. Yes, we didn't do that here.
No, I understand, but I'm just pointing out that for phonetics they know about this. Right? So if you want to know about what are the kinds of mistakes that people make, think about mistakes as a fact. Then you could go to the phonetics people and say, look, what are the kinds of mistakes that people actually make? And they'll say, well, anticipations and perseverance. Maybe there are more.
That is a good suggestion. Yeah.
I had another question. This is something completely different. So I guess with verification, it's like a binary thing, right? You either verify it or you don't. But in my mind, I'm not sure how these things work, but I can imagine that if something actually fails to be verified, it will take longer And the verification, successful verification is true, or still the way around?
It is the other way around usually, because actually the property is split most of the time. So for it to be fair, you just need to find a counterexample. While for it to be successful, you need to not find any counterexample.
Because I can imagine that has an effect on
Yes, it can
the kind of rectangles you choose has an effect on the speed by which and what you want. If there's a problem, you want to find it as soon as possible. If it's good one, I guess then you need something more exhaustive than anyone, right?
Yeah, that is the case.
And your story is basically that if it isn't good, right, you cannot cover it, you will find a typical very quickly.
I don't think I'm concerned with speed here. We just hope, because one thing to say is that this is one of the first kind of verification applied to NLP. So we're just like exploring the field and trying to get as much as we can. So it's still not much concern with speed for now.
Yeah, but honestly, timeout.
Yes, so
you have timeout. So basically, then speed is a matter because then the fact that you don't get an answer is because
for the size verified model, yes. So the other one that is less precise and we think the result, it never finds out. It's very fast that way. And maybe the best option is in the middle, a more precise one, but still kind of faster.
Well, I think the kind of I can't remember exactly how you describe it, but you have this title right thing. You have a number of choices. You had a number of choices at some point where you say, well, I can do big rectangles, I can do short rectangles, right? And I can imagine that the operational profile of the system that you actually need for verification actually implies what it would work best for them.
Yeah.
That's my suggestion.
Yeah. No, this is certainly something we have to take into account. Yeah.
Can I ask you a very good question? If you were to wait for longer, will you get like the verification accuracy?
Some of them.
Repeat the question for people in Zoom because I don't think they hear very well when they.
Okay. Yeah. So the question is, if we wait for longer, do we get further results? The answer is yes. We will get more results. We just don't know how much longer because most of the queries are quite fast anyway. It's just, I think about like 4% that I'm out. If I remember correctly from what Tommy told me. So yes, he said like he set a maximum of 1 hour per query limit. You can have 24 hours or however you want. It's just so many queries with that framework that it took 1 week to do them all. In parallel, like it has thousands in parallel in the cluster. Yeah.
So, I think this is related to this question. Are building these rectangles typical, computationally expensive for them?
So the question is how difficult is computationally or expensive to build these rectangles? It's not at all computationally intensive because for all the points inside, or not all the points inside, all the points that you want inside, all the red ones, for each dimension, you calculate the minimum and the maximum, and then you just take the minimum, the global minimum and maximum, and let's say so this here is like the minimum of this point, this one here is the minimum of this point, stuff like that. So that's why we work with alpha rectangles instead of convex modes, because it was computationally not even feasible, it's just very easy.
But I guess it's easy to search for the nice rectangular representations so that you can have like.
Yes, the challenge here is to come up with some meaningful representation, but when you have that, it's so fast.
But some representations can be more easily verifiable.
Yes, Yes,
So
this one,
I can also imagine that maybe, so I don't know, maybe the number of rectangles can be an important factor. It can also be that the size of the rectangle is an important factor. I don't know. But what
So
you told
the
me, why is it
number,
important?
I mean, I don't think the number is that important. You just, the idea is you want the biggest one you can get, but since quite difficult to verify such big rectangle thing.
So if you go back to this slide,
Yeah.
you could say, let's take the bottom one, right? You could also say that these two rectangles
Yes.
side by side.
Yeah.
I have no idea how the
Yeah,
asymptotic
that
performance
is
of
true.
the system is.
That is
So it
true.
could be that having two side by side, that two separate queries, could be faster than doing the big one in one go. But or maybe it's the other way around. I don't know. Maybe you know.
I mean, since if you do it in parallel, it's probably faster. I mean, not necessarily, but
Not necessarily.
not
I mean,
necessarily.
this is not the only one. You would have thousands of them, right?
Yeah.
So you can certainly do all your.
Yeah.
You don't need to split it up just to get more performance out of it in terms of prevalence, I imagine. But it could just be. I mean, if you say it is, let's say, cubic in the size or in the volume or something like that, then you might say, well, actually, it's better to start with small ones and work my way upwards. Instead of big ones, it's shrinking my way downwards.
That is a good point. I don't think it is that way because Marabou does calculation like so that the big point is they split. Maybe some of the correct example, but they split the case when they found the ReLU activation node. So it is dependent of how many activation nodes you have more than the size of the size of it. Yeah, that's my intuition.
In our last slide, on the future work, you suggested ways to improve third step, but other ways you think you could improve by having steps that prove each other. Like for instance, would that be useful to know, like to target specific attacks and link them to specific models to see where things work best?
Yes, that is definitely the situation, the case. Sorry, maybe yeah. Actually, it is the case because, for example, this attack then I used here to draw up rectangles and define neural networks. So it is already kind of linked, and you can intertwine them. And yes, it's definitely not only. You can go in a few ways. Yeah, it's the attacks can be used.
Did you look at the sort of models that apply best to specific transformation, not the whole body of attacks, but just part of them?
So let me see if I got it correctly. So our actually best two networks are these two, and they are much better than the others. And the best performance they get is on these hypersatellite rectangles. But yes, they also so some models might perform better on some hyperrectangles than others. Is that what you asked?
Yeah, for me it was more whether we could reach a higher percentage if we were looking at some a different form, a different set of word effects.
Oh yeah, definitely could be. Yeah. So we just selected some that for us make sense, but then maybe all different type of attacks or even the same type but different subtypes. So yes.
So when you identify something, especially in this scenario, $100 question is not whether 100 sentences can be verified to be robust, but how many unseen sentences you have within the rectangle. So can you give a sense of how many, what are the orders of magnitude of new sentences that we have in the shapes?
Yes. That is a good point. So as I talked at the beginning, as I said at the beginning, we don't think epsilon cubes are fit for this task, also because they don't find inside other unseen sentences, or many of them, right? We actually had, it's not here in the slides, but we actually calculated, for example, for word attacks, how many, you just take all your inputs, you get a lot of perturbations, like I think we got 150,000, something like that. And then we just take hyperextenders and we say how many of these new sentences that we haven't seen are inside. With this one, it was some of them, like maybe a few thousand, but percentage-wise, it's not much. While this one, I don't remember exactly the number, it's like tens of thousands, but it was around 50%. So this one contains around like 50% of unseen perturbations inside.
When do these unseen, for example, for dataset or something?
Yes, but we perturb it randomly. So new perturbations that they haven't seen.
Can I something more about that? How do you make sure that there's syntactic, for example, that they maintain?
Yes.
How do you actually use perturbations and that way for what you would say? And when you break things like calling priors, like having a prior what humans would do, which I guess more phonology and connection in the space here, like typing is a prior, word substitutes, there are not calling the prior in grammar, for example.
So we manually look at sentences. I was working with Stanley on that. It's not done yet. We this couple of weeks we plan to do it, but we just manually look. So we had a quick one, and that's where we got that word and character attacks work quite well for the Alibaba dataset, but word attacks don't work well with the medical dataset, while the more sophisticated sentence ones, yes, they do. They're not perfect by any means, but we're gonna have a manual evaluation of that. We cannot do an automatic one.
Why not?
Well,
Why not use like the language model note, for example? It would be an indicator to get you a filter so that you can do more. Like the language model says, oh, the launch mark 100.
yes, no, actually, I think we were, another question we were also planning on using GPT to calculate.
The likelihood of the same.
Yeah, it was one of the, I don't remember exactly the name of the metric, but yes, we were also using it. So manually and this GPT-2, I believe. Yeah. Yeah, sorry, you're right. Yeah, well, you don't have any other questions, then thank you for coming.